All right, this is lecture 4, which is going to be on understanding the size of sets, essentially. How do we compare when two sets are the same size? What does that mean? And sort of the formalization of that is something called cardinality. And so cardinality concerns when two sets are equivalent. And in particular, we want to understand better what we mean by a set being finite. And then we'll also introduce terms like denumerable, countable, and infinite. And we'll also gain a deeper appreciation for the difference between real and rational numbers before we're done here today. Okay, so to start with, here's the fundamental definition. Two sets A and B are said to be equivalent if there exists a one-to-one correspondence between them. In other words, if there's a bijection from A to B, a one-to-one in onto map, then A and B are said to be equivalent sets. So a silly example of this, and sorry, I still haven't gotten white out. I went to Walmart today and I completely forgot. My bad. But in the meantime, I'm using sticky note editing, so it'll work. There's a typo in the posted PDF in the in Blackboard. You'll find it. So I fixed the mapping here. F of 1 goes to 1. F of empty set goes to 2. F of Dora goes to 3. See, I must have written these notes around the time my daughter was watching Dora the Explorer, which is a horrible show. But anyway, so this mapping F is injective and it's surjective, and it proves that the set A and the set 1, 2, 3 are in fact equivalent. So you can repeat the same idea for a finite set which has k things in it, and I use this notation here, n sub k, natural numbers from 1 to k, and we're going to say that the way we will define something to have k objects in it is if there exists a bijection from 1 to ... k to that set. I mean, if there is, then we could make the bijection basically psi of the j thing in the set equals to j. And that's going to give us a one-to-one and onto mapping if there actually are k things in the set. So anyway, I'm just trying to motivate for you what we mean for a set to be finite and have k things in it. The way to formalize that is to insist that that the set permits a bijection to this particular model of k things, namely the natural numbers 1 through k. In Pete Clark's article, he talks about a hypothetical shepherd not having numbers but having a bag of stones and using a bag of stones to count the sheep. So you could think of these the n sub k as sort of our bag of stones to count k things, I suppose. I don't know, whatever. Anyway, it's a benchmark for sets with just k things. And so we use that to make a careful, somewhat careful definition, I suppose, of a finite set. Here it is. So, and we'll also introduce cardinality right here. So the cardinality of n sub k is k. All right. So cardinality to start with is just ordinary, plain old garden variety counting. And a set S is said to be finite if and only if it's either empty or in one-to-one correspondence with n sub k for some k in the natural numbers. Moreover, we define the cardinality of A to be A bar bar. So I'll do A with a double bar over top to be the cardinality. That notation is not universal by any stretch of the imagination. I think my brother uses card of A in that paper I've posted in the additional reading. So, like that. There are various notations, but that's the cardinality of A, and it's just defined to be k when A is in one-to-one correspondence with n sub k. And if the set is empty, then we define the cardinality to be 0. All right, great. So let's move on here. So, definition. What about infinite sets? Well, this may not be a very satisfying definition to you, but here it is. An infinite set is one which is not finite. Okay, great. So, okay. So what else can we say? Proposition. A finite set is not equivalent to any of its proper subsets. So remember, a proper subset, if we're talking about S is a set, right? And then a subset of S is proper if A is not equal to S, right? So a proper subset can't be the whole superset. And this proposition says that a finite set is not equivalent to any of its proper subsets. At least one thing I read, I can't remember where I read it, but somebody I was reading, either my brother or Pete Clark, I think, said that this could actually be used as a definition for finite sets if you wanted to. But anyway, I like our definition for finite sets. So now that I'm not going to, like I said, I'm not going to prove everything here, but you can prove that a finite set is not equivalent to any of its proper subsets. And so the contrapositive of this is proposition 1.6. Now, if you forgot what contrapositive is, or maybe you just never were told, which is possible, I suppose, I've included a footnote down here to try to unwrap what I mean by that. Let me go through my footnote right quick. So here's the footnote. In logic, the contrapositive of P implies Q is that not Q implies not P. In symbols, P implies Q if and only if not Q implies not P. So this is the not Q implies not P is the contrapositive of P implies Q. So in the thing we're looking at, P is the statement a finite set, whereas Q is the statement is not equivalent to any of its proper subsets. So not Q would be, the negation of a set is not equivalent to any of its proper subsets would be there exists a proper subset for which the set is equivalent to the whole set. There exists a proper subset for which the set is equivalent to, and not P would be that the set is not finite, which is to say it's infinite, right? So that's proposition 1.6, in fact, which is the contrapositive of proposition 1.5, namely a set which is equivalent to one or more of its proper subsets is infinite. And that's pretty neat because it gives you a kind of cool way to show things are infinite. If you can just find a proper subset which is equivalent to the given set. So if you're counting, there are two nice ways to show a set is infinite. The first, you could assume that it was finite and work towards a contradiction. Second, you could find a bijection from the set to some proper subset of itself, which is what my next example will show. Here's a proof that the natural numbers are infinite. You can consider the mapping f of n equals to 2n. This is a bijection. So 2n is the positive even numbers, all right? If you look at f of x equal to f of y, we've got 2x equal to 2y, which implies x equals y. What does that prove? That proves that f is 1 to 1. And next, to see that f is an onto mapping, if you pick anything in 2n, it has the form 2k, right? So you can pick k in the natural numbers such that y equals to 2k, which is to say that f of k is equal to 2k, which is equal to y, which is a very, very wordy proof that f is in fact surjective, it's onto. So f is 1 to 1, and it's onto, therefore f is a bijection. And of course, 2n is not all of n, right? Because 2n doesn't have odd numbers. So it's definitely a proper subset of the natural numbers. And thus we have proved that the natural numbers are infinite. And I like this proof a lot because while contradiction is often very useful in mathematics, it's also kind of, I don't know, I don't enjoy proofs by contradiction. I like proofs that are constructive like this more so. I guess it's not exactly totally, well, anyway, I'll move on here. So next up, countably infinite sets. Definition. So again, a lot of this lecture is just introducing you to some terminology and just trying to make you aware of just some of the current, well, not really so much current, but ongoing discussions that there are in mathematics concerning these things. All right, so, and I'm actually kind of surprised that the book that I chose for you, that was the mathematical analysis one, I guess it is. I'm surprised that there's not more of this discussion in there. It's pretty typical for a real analysis course to talk about some of this, especially if this course is like your first course on proofs. It's it's kind of customary. But anyway, denumerable. So a set S, we'll say S is denumerable if and only if S is equivalent to the natural numbers. All right. And the cardinality of a set which is equivalent to the natural numbers is said to be aleph naught. I think you could write it like this, aleph. It's read aleph naught. Like that, and I'm still not quite doing it right. In any event, so the cardinality is aleph naught if and only if the set is equivalent to the natural numbers. Now, there are many more sets with the same size as the natural numbers than you might think. In fact, all of the following are the same size, same cardinality as the natural numbers. The natural numbers, of course, that's stupid. Even positive numbers, multiples of 3, the integers, the even integers, the Cartesian product of n and n, the 123rd Cartesian product of n, the solution set to sine x equal to 0, the sequence of numbers of the form 2 over n, such that n is a natural number. All of these have the same cardinality. And I think I have misspelled it here. My apologies. I didn't get all of those. I sometimes forget to put the I, and that's kind of how I say it. But I think it's cardinality. But I tend to shorten the word to cardinality, which I think is wrong. It's technically cardinality. All right, I shut up. But the reason that all of these sets are in fact the same cardinality as the natural numbers is because essentially you can find a way to list the elements in these sets. And if you can find a way to list all of the elements in the set uniquely, then there's a natural one-to-one mapping you can form with the natural numbers. As I point out, these are all discrete sets in the sense that like the points in them are separated, What I think is much more surprising is that the rational numbers rather, it turns out they are also, to me this was shocking when I first learned it, but the rational numbers also have cardinality aleph naught. They are equivalent to the natural numbers. And that to me is really surprising. For one thing, is because the rational numbers, look at this. So if you take any two rational numbers, so p over q and m over n and q, you can find another rational number between these two. You just look at the midpoint, 1/2 of the, that plus that gives you the midpoint between those two on the number line, right? Like, here's p over q. Here's m over n. All right. This guy right here, he's in the middle. All right, the midpoint. And you can see, plain as day right here, that when you add these two together, making common denominator, you yet again get a rational number. So between any two rational numbers, there is another rational number. And if you were to pick the midpoint in that one, there's another one in between those, and you just keep going and going and going. So rational numbers are not like these guys in the sense that these guys are kind of spread out, right? If I was to make a picture of these, they're for the most part spread out. Okay, admittedly, this sequence 2 over n, it is kind of bunched up. When you get towards n goes to infinity, you kind of, okay, can't find that. Maybe these are not discrete. I guess I should say this guy is not manifestly discrete. In fact, I think this one's not discrete. Anyway, it definitely has something going on at 0, which is unlike these other ones. Okay, we'll make that very fuzzy comment more rigorous as this course goes on. But anyway, so you're like, okay, well, that's a great claim that you're making, that the rational numbers, are the same size as the natural numbers, that they also have cardinality, if not. Well, you might have guessed by now I'm not going to prove it on this handout, right? But it is true that the rational numbers have the same cardinality as the natural numbers. Now, I did print out my brother's wonderful paper that he wrote with Mike Bosse, who's also at Appalachian State. I think technically this is part of a paper they're trying to publish right now, so don't share it too widely. But actually, I mean, you can probably share it with whoever. This is pretty wide. I mean, this is not theirs. This has been known. I think this is Cantor's. Cantor did a lot of the important early work on this stuff back in the end of the 19th century. But here we can make this swirly path through the grid of integers, right? And as you go around here, this gives us a way of listing rational numbers. And so there's some rules here, right? So the rules for setting up the mapping is, first of all, we're going to ignore the points which don't correspond to rational numbers. Namely, on the x-axis we have division by 0, so we set those aside, and we're gonna go around. This is the fraction 1 over 1. There's the fraction 0, fraction minus 1 over 1. Here's 2 over minus 1, which is minus 2. 2 over 1, 1/2, right? Now we're skipping over 2 over 2 because that's 1. We already got that back here. Now we're skipping over 0 over 2 because that's 0. We already got it here. And then minus 1/2. Okay, we'll pick up that one. That one's new. And then these we ignore because we already have those. Minus 3/2 we didn't get yet. Minus 3 we didn't get yet. 3/2. Get over to 2/3, 1/3. And so as you keep traveling out, you will pick up all possible fractions. And it's obvious that you can put them into a list, right? And if you can put them into a list, then you can define a one-to-one mapping, one-to-one correspondence between making the first thing in the list go to the first thing in the natural numbers, the second thing in the list go to the second natural number, the third go to the third natural number, and so forth. That's how you define the bijection, just by taking the list and defining the bijection by just sending the first thing in the list to the 1, the second thing in the list to 2, and so forth. That defines a bijection between the rational numbers, in this case, and the natural numbers, which proves that the rational numbers are, in fact, the same size as the natural numbers. They have cardinality if not. Now, so in other words, the rational numbers are denumerable. They are countably infinite, you could say. And so here's another definition. A set S is said to be countable if it's finite or denumerable. If a set is not countable, it's said to be uncountable. So countable includes the case that it's denumerable. In other words, that it's the same, let's say cardinality, the same size as the natural numbers, or it's finite. And I guess I should warn you that Pete Clark's articles, he uses countable in the place of countably infinite, which is something some people do. So just beware. There's some disagreement on what count. Some people include finite and countable, and some people don't. We will include finite and countable. So either a set is either countable or it's uncountable. If it's uncountable, that means it is, in some sense, bigger than either the natural numbers or a finite set. All right? Now, so what can we say about these uncountable sets? So I've titled my next section Uncountably Infinite, which is a little bit redundant because every uncountable set is necessarily infinite. All right. A countable set may or may not be finite, but an uncountable set is definitely not finite. And one of the theorems that you can prove, and I don't think this is a particularly easy theorem to prove, but it is a theorem you could prove. The open interval from 0 to 1 is uncountable. All right. And so I think I have a proof that I can show you of that. It basically stems from the decimal expansion of the real numbers. It's theorem 2.5. Again, this is from my brother's paper on types of infinity, current title, with Mike Basset. Set of real numbers is uncountable. So I guess they just pick on the interval from 0 to 1, 0 included to 1. And so I think this is proof by contradiction. He says, suppose R is countable. That means every subset is countable. In particular, this interval from 0 to 1 is countable. This means we can list the elements of I in some order, 1, 2, 3, and so forth. But every real number has a decimal expansion, right? In fact, you can give it a unique decimal expansion if you don't allow for trailing nines. So, for example, 12.3999999999999, we are just going to say is 12.4. We will not allow the trailing 9 expansion, all right? And that way we'll have a unique decimal expansion for 12.4. So it says consider x sub j and I. So it's between 0 and 1. Expand x sub j without trailing nines to get the decimal expansion. X sub j is 0.d1j, d2j. These are the decimal places, right? Which this, if this is the decimal expansion, that means it's d sub j over 10 plus d sub j2 over 100 plus d sub j3 over 1,000 and so forth, right? Where each of these d sub j whatevers is an element of 0 to 9. It says, okay, so focus on the ith decimal digit, of the ith number. That's a mouthful. Of our, oh, I do have it. For a second there, I thought we were going to have to stop. List, like this, so he's like, look at D11, D12, D23, right? And he says, define y sub I to be 1 if y sub I equals 0, and y sub I to be dii minus 1 otherwise. Then y, where's this y coming from? Sorry, I've lost my place here. Must have been y back here somewhere. Now focus on that. Oh, I'm sorry, he's defining y. If I could just read, define y sub I to be 1. If y sub I is equal to 0. I think that's a typo. I think that's supposed to be if I equals to 0, maybe. I will have to tell my brother about this. Anyway, and define it to be dii minus 1 otherwise. Then, well, oh, anyway, let me go on here. So then y is equal to 0, y1, y2, This is a real number in here, and we choose y's digits so that it does not trail and end in trailing nines. This also keeps us from getting 0.999 repeating as 1. And notice that y is not equal to x sub I for each I. Since y and x sub I have differing ith digits, thus y is not on our list. Y is not on the list, and so our list is incomplete, which is a contradiction. So I may just be too tired. I mean, I don't quite follow, but that doesn't mean it doesn't make sense. It's just, like I said, the proof that 0, 1 is uncountable, something like this. It actually gets into like the, dirty decimal expansion and the proof by contradiction, something like that. I'm just going to leave it there for now. And Anyway, but once you know that the open interval from 0 to 1 is uncountable, it's easy to prove everything else is as well. So we can, because I can come up with bijections from the open interval 0, 1 to a lot of other things. I have at least one of those down here. We'll get to that in a second here. First of all, the definition. So we define aleph naught, remember, to be the cardinality of the natural numbers. We're going to define C, or the continuum, to be the cardinality of the open interval of 0 to 1. And in fact, that will be the same as the cardinality of the real numbers, because we're going to find a bijection from 0, 1 to the whole reals. Before I do that, and maybe I won't do that, I can't remember, but you could easily trade 0, 1 for some other open interval. You can just use the linear map, well, technically a fine map, mx plus b, and so f of 0 is 5, f of 5 is 8, so I'm basically mapping 0 to 5, and well, that's no good. Why did I put 5 here? Goodness gracious, guys. This right here, I feel like it should be a 1. I would like to send, basically what I want is I want f of 0, 1 to equal to 5, 8, okay? So that means, among other things, f of 0 should be 5, great, that I agree with. F of 1 should be 8. So this shouldn't be 5m plus b, this should just be m plus b. That 5 should not be there. Which says to me that m equals to 3. So that 5 does not belong there. So f of x equal to 3x plus 5 will provide the bijection, in fact. And you can easily check that, right? When we plug in 0, we get 5. When we plug in 1, we get 3 plus 5, which is 8. And you can also kind of see that graphically. Anyway, sorry about these errors. You can blame my previous students for not pointing them out to me when I did this before. Or maybe they did and I failed to correct them. Let's assume that. Anyway, so it's fun to try to show bijections between different subsets of real numbers. But, it is a theorem that all of the intervals, any interval of real numbers, in other words, a connected subset of real numbers, other than the singleton, all right, so like any of them that are more than just 1 point, they all have the same cardinality. They're all equivalent. There's a bijection between any two of those, which doesn't mean it's easy to find that bijection. Here's the bijection between 0, 1 to the reals. First of all, of course, I can take 0, 1 to minus pi over 2 to pi over 2 by using the construction in the previous example. And then I can use inverse tangent. Inverse tangent will take minus pi over 2 to pi over 2 to the reals. So, because remember, the inverse tangent is the inverse for tangent from between the vertical asymptotes, minus pi over 2 and pi over 2 for tangent. And so if you look at the graph of inverse tangent, it's like this, right? And it goes to pi over 2 that way, and it goes to minus pi over 2 that way. Inverse tangent has the domain of the reals, and it has the range of minus pi over 2 to pi over 2. And so you can prove that inverse tangent is a bijection from minus pi over 2 to pi over 2 and the reals. And as such, it proves that the cardinality, those sets, that the reals is equivalent to that minus pi over 2 to pi over 2 set. And then we also, from the previous example, could prove that 0, 1 is equivalent to minus pi over 2 to pi over 2. But we can compose the bijections if we like, and get a bijection directly from 0, 1 to the whole reals, combining these two. Because remember, the composite of bijections is a bijection. We learned that last time. And that, in turn, says that if A is equivalent to B and B is equivalent to C, it follows that A is equivalent to C as well. There's a transitivity of equivalence of sets. And that rests on the fact that the composite of bijections is a bijection. Apparently, I'm proving here that mapping F is in fact injective and surjective. So now I will say this: if you can find me an explicit formula showing that the half open, half closed interval A to B is equivalent to the closed interval to A to B, I would give you some points. All right? And I'm not saying that's impossible. I'm just saying it might be tricky. So next up, we have Cantor's theorem on transfinite arithmetic. All right. So here it is. Let A and B be sets. Well, this is not the theorem, actually. This is the definition. So sorry. So first of all, we say that the cardinality of A is equal to the... Remember that the cardinality could be like Aleph naught or C the continuum, right? So there's not a natural idea of equality there just yet, and we're going to try to define it as such. Cardinality of A is equal to cardinality of B if and only if A is equivalent to B. Otherwise, they're not equal. The cardinalities are not equal. The cardinality of A is less than or equal to the cardinality of B if and only if there exists an injection of F from A to B. The cardinality of A is less than the cardinality of B if and only if the cardinality of A is less than or equal to the cardinality of B, right? In other words, if there exists an injection from A to B and the cardinalities are not equal. All right, so notice that the injection doesn't, it has to take A as the domain, right? And so there's not an assumption that it hits all of B, so this F wouldn't necessarily be a bijection, right? Now I should mention transfinite arithmetic enjoys many of the same rules as ordinary arithmetic, and I think those are actually developed in the additional reading if you're interested. But this is a big one. This is a big one here. Everybody should see this. Cantor's theorem. Cantor's theorem says the following. It says for every, because once you have this, just, oh man, all kinds of results follow. For every set A, the cardinality of A is less than or equal to the cardinality of the power set of A, right? So, for example, the cardinality of the natural numbers is less than the cardinality of the power set of the natural numbers. That's supposed to be P. Remember, the power set is the set of subsets, right? So the fact that it's less than or equal to, that's pretty easy, right? If you have a set A and you want to show that A is less than or equal to the power set of A, you could just use the following map. You could say F of X is equal to the set containing X, right? That is definitely an element of the power set of A. And it's easy to prove that that mapping is an injection. So it's almost trivial to prove that A is less than or equal to, that the cardinality of A is less than or equal to the cardinality of the power set of A, because this mapping member goes to its corresponding singleton in the power set is an injection. But the fact that they're not equal, well, that was the genius of Cantor. All right. I don't think it's terribly difficult to prove, but I'm really going to focus more on the application here. So Aleph naught we define to be the cardinality of n. That will be less than the cardinality of the power set of the natural numbers, which, by the way, would be less than the cardinality of the power set, which would be less than the power set of the power set of the power set of the natural numbers, and so forth. So, okay, great. then the next question people usually ask is, what about the real numbers? What about the size of the real numbers? Where does the continuum fit into this picture, right? So it can be shown that the size of the natural numbers is less than the size of the continuum. In other words, you can find an injection from the natural numbers into the real numbers, and you can also prove that, of course, the cardinality of the real numbers is not equal to the cardinality of the natural numbers. Remember, we proved, actually, well, we didn't prove, but I half showed you the proof that 0, 1 was uncountable, which is to say that it does not have the same cardinality as the natural numbers, among other things. So that essentially proves that the aleph naught is less than C, right? Here, I mean, this is so that's pretty interesting. Now, I haven't answered the question where aleph naught fits yet, have I? I mean, where the continuum fits yet. But the Cantor-Schroeder-Bernstein theorem says that if the cardinality of A is less than or equal to the cardinality of B, and the cardinality of B is less than or equal to the cardinality of A, then their cardinalities are equal, right? And remember what that means. That means that the set A and the set B are equivalent. All right. So this is a non-trivial theorem. There's a proof written by my brother, posted in the additional reading folder, and there's also a proof in one of the articles I posted that are written by Pete Clark. But here's an application of the theorem. Since we can show that the cardinality of the power set of the natural numbers is less than or equal to the cardinality of 0 to 1, and we can show that the cardinality of the power set of the natural numbers is greater than or equal to the cardinality of 0, 1, it follows that the cardinality of the power set of the natural numbers is equal to the cardinality of 0, 1, which we've already shown is the same as the cardinality of the reals, using that inverse tangent and the other thing we talked about earlier. And so what I'm saying is that this shows that, in fact, C fits right about here. This is C. The continuum is the next one in that list there. Now, okay, great. So note to self, the phrase we means students in the sentence above. Turn this into a homework problem. Ooh, there's a threat. So I'm going to try to make this into a homework problem, but I think I need to give you a little bit more guidance than just say, prove this and that, I think that would be kind of mean without without a little bit of guidance there. So stay tuned. All right, I will eventually give you homework. You guys are still not emailing me. Hey, where's my homework? Where's my homework? You didn't give me homework. But don't worry, I will not forget. All right. So definition, trichotomy property of the natural numbers. Given two natural numbers, they're either equal, or one is greater, or one is less than the other. And there's something similar for cardinality. A and B are any two sets. Either the cardinalities of A is larger than the cardinality of B, it's equal, or the cardinality of A is less than the cardinality of B. So cardinality is, in some sense, similar to natural numbers. It has this comparability, this trichotomy property. And that said, well, I say that this theorem is true, but it turns out that this comparability theorem, which seems eminently reasonable, is impossible to prove in ZFC, in Zermelo-Fraenkel set theory, unless we assume that the axiom of choice is true. Now you might ask, what's the axiom of choice? All right, well, great. What's the axiom of choice? The axiom of choice is this. If you have a collection of non-empty sets, then there exists a function f, which we call the choice function, from A to the union of A and A. such that for every A in that family of sets, we have f of A as an A. This is a very fancy way of saying that if you have a collection of non-empty sets, you can like pick something from, you can choose one, choose an element from each one of them non-empty sets. It's called a choice function. And this axiom of choice, it does lead to some unusual results. For example, the Banach-Tarski, I mispronounced that horribly, paradox says that a ball can be cut into pieces and reassembled into two balls such that the total volume is doubled. That's disconcerting to some people, but not so much to me because the cuts that are involved are not really physically reasonable. They're just some sort of mathematical oddity, really. And also the weird result, this is more bizarre, the weird result, every subset of the reals can be reordered such that it has a smallest element. Now that's one of those things that people say, but ask them to do it and they can't. Theorem. If there exists a function from a set A onto a set B, then the cardinality of B is less than or equal to the cardinality of A. So if there exists a surjection from one set to another, that means that the domain set is at let's see here. It means that the range, the set and the codomain rather, cannot be larger in terms of cardinality than the domain. So surjectivity suggests that there's at least one thing in the domain to map to each element in the range. Of course, it could be the case that more than one thing maps to each element in B, but certainly one thing in A maps to a given element in B. So if the fibers of A are really big, then the inequality would be exercised here, and it would become a strict inequality. But anyway, the proof of this theorem given in the text, that is I'm sorry, I meant to edit that out there. My apologies. There is no proof of this theorem in your text. I will confess this, though. We actually used the axiom of choice when I discussed how to construct a bijection from an arbitrary function, because if you look at what I did there, I had to pick something from each fiber in order to find that subset of the domain, which makes the function into an injection, right? So we actually use the axiom of choice in places where you might not have noticed. It's often used. But it does come with a little bit of heartburn theoretically because it has strings attached. But it does seem like something that, I don't know, like most people don't really worry about this stuff. We just kind of do things which make sense and hope the foundation stuff works out. But I will admit that's how I function. Continuum hypothesis. Well, the continuum hypothesis states that continuum C is the next finite number beyond L if not. In other words, there is no other infinite set between the rationals and the reals, in the sense that there does not exist a set that is somehow bigger than the rational numbers and yet smaller than the reals in terms of cardinality. This was conjectured by Cantor back in the 1900s. Late 18th century, I should say. But only later did the work of Gödel and Cohen in the 1960s elucidate the issue. Gödel showed that the continuum hypothesis was undecidable, but relatively consistent in Zermelo-Fraenkel set theory. But then later, Paul Cohen showed that the continuum hypothesis was independent of the axiom of choice relative to Zermelo-Fraenkel set theory, modulo the axiom of choice. So the continuum hypothesis and the axiom of choice continue to be widely believed since they are important big guns for certain crucial steps in hard theorems. But basically this has opened the door for asking the question, are we thinking about set theory correctly? Like, what are the axioms of set theory? Is there one set theory? Are there more than one set theory? Is there, do we have different choices for the foundations of set theory? I am not an expert in this area, but I will tell you that there are open questions, all right? And so I actually included a PDF of the axioms of Zermelo-Fraenkel set theory in the additional reading, just in case you're interested. But we're not going to keep diving into this direction in this course, but these are things we should be aware of because, they're part of the mathematical culture and discussion, and I would say that this is sort of part of your liberal arts education from a mathematical perspective. I'm trying to get you to be a little bit more well-rounded, certainly more well-rounded than I have been at various points in my mathematical education. So anyway, I hope you've enjoyed this, and I will, again, try to make you some reasonable but interesting homeworks from this material sometime soon. Thanks.